Let's look at something called the p-series. It's the sum from n equals 1 to infinity of 1 over n to the p. P has to be a constant here. It can't change with n, and it has to be bigger than 0. And then there's a generalized version of that, which just has a linear function of n, and then take a power of that. Again, p has to be constant, bigger than 0, and the a and the b have to be constants. They can't change with n. It turns out that either of these series converges when p is greater than 1, and diverges if p is less than 1. If p is greater than 1, you still have to worry about divide by 0 in this generalized p-series, but we basically never have to think about that. We just don't think about problems where b would be negative or a would be negative. So that's called the p-series test, and the proof of it we'll actually see in chapter 8.3. A very fairly simple version of a p-series happens when p equals 1. That would give us 1 over 1 to the 1 plus 1 over 2 to the 1 plus 1 over 3 to the 1 plus 1 over 4 to the 1, etc. And so that's just a half, 1 plus a half plus a third plus a fourth, which we could write this way: the sum n equals 1 to infinity of 1 over n. And that's called the harmonic series. It's called harmonic because it's vaguely related to the harmonics or the overtones of like a guitar string that you would pluck. You would have the whole thing vibrating plus a wave that has half the wavelength plus a wave that has a third of the wavelength, and so forth. As far as I know, in music and acoustics, there's no reason to add up all those wavelengths, so it's not a very strong link between the harmonic series and harmonics in music or acoustics, but it's the name we have. And what would you say, does this series converge or diverge? Well, it's a p-series with p equals 1, and the p-series test says that if p is equal to 1, then the p-series does not converge. There's no less than, greater than, or equal to here. So the harmonic series famously diverges. Since p equals 1 is not greater than 1, like we said up there. There are proofs of that even without the stuff we're going to do in chapter 8.3, but I don't think we need to get into them. Let's play around with the p-series idea a little bit. Let me give you a problem. So does this series converge? Well, 1/10 plus 1/20th plus 1/30th plus 1/40th plus dot dot dot. So take a sec to think about that. Is that a p-series? Well, let's see, the sequence goes to 0. Does that guarantee that the series converges? Like 1 over 20, 1 over 30, 1 over 40, those are getting smaller and smaller, going towards kind of y equals 0. So does the sequence going to 0 guarantee that the series converges? The answer is no. There are plenty of series where the sequence goes to 0, but yet the sum of all those numbers is infinite. So I'll write a big nope here. It also doesn't guarantee that the series diverges. It just isn't enough information at this point. What else can we say? Well, we could say that this sequence, or the series, we could write it as 1 over 10 times 1 plus 1 over 10 times 2 plus 1 over 10 times 3 plus 1 over 10 times 4, etc. So we could say it's the sum of 1 over 10n, n starting at 1. And we could say that's the sum of 1 over 10 times 1 over n. I'm going to start leaving this just a sum. It defaults to be 1 to infinity. This is a constant times each term, so we can factor out that constant multiplier just like we would for a non-infinite sum. So I get 1/10 times the sum of 1 over n. What is the sum of 1 over n? That is the harmonic series. And the harmonic series diverges. Does 1/10 the harmonic series diverge? Well, the harmonic series is infinity, 1/10 of infinity, still infinity. So overall, the series diverges to infinity, not the oscillating forever kind of without settling down kind of diverging. So that's one way we can think about using the harmonic series. It can kind of pop up in disguised forms like this. Here's another interesting problem. What if I don't start at 1? What if I start sometime later, like at n equals 100 or 1,000 or 1,000,000 or whatever? Here I'm just doing the harmonic series, but not all of it, just part after n equals 100. Or what if I'm doing a p series? What can we say about whether these summations converge or not? Well, we can say this thing, how does that relate to the whole thing? We could say the sum from n equals 1 to infinity is the sum n equals 1 to 99, for example, plus the sum n equals 100 to infinity. And this is just the sum of 99 different numbers, and if they're 1 over n or 1 over n to the p, each of them is just a plain number, no infinities in there. So this is just some finite number. So if you had this, you could say, well, that's just the original series plus some finite number. So we could say this or this is like that one. So if the overall sum starting at 1 diverges, then this side diverges too, and this side is just some finite number plus that. So then any sum that's missing the first few terms will also diverge, right? And here is some blank number. It's just some number, just as long as it's not infinity. It could be 100, it could be 1,000, whatever. Since that whatever it's missing is just some finite number, it can't kind of make up the difference between the infinity answer we get over here and what we might be thinking we'd get over here. Do you think this idea works with if the infinite sum converges, then any sum missing the first blank number of terms will also converge? As long as we don't have any infinities in the middle and negatives canceling, negative stuff canceling each other. And here I said if the infinite sum diverges, then any sum missing the first some number of terms will also diverge. Do you think it works the other way, that if the kind of tail converges, then the original has to converge, and if the tail diverges, then the original has to diverge too? And it works backwards. If the tail sum, and by tail I mean like starting at some value other than 1, the sum starting at 1 also converges, and same for diverges. So as long as you don't have any divide by zeros.